roses, these definitely are harder than what we've been doing. So we're going to make 3 columns here. So this is, and now we're going to move on to 4 columns for other shapes. Like I said, it gets harder.
What's the third column called?
2 theta. Whatever the argument is. So keep in mind that you are graphing a polar grid by definition is r comma theta. That doesn't change. So you're still graphing r theta, but you are using the 2 theta because that's the argument to evaluate the function. So I'm not evaluating it at theta because the function's not theta. It's r. It's cosine 2 theta. So I need to evaluate it at 2 theta. So
First robotics yearbook to the gym for pictures.
if you need to come and go, please come and go quietly. I know there's people coming and going all day. So what are good choices for 2 theta because it's a cosine graph? Yeah, 0 still for everything. Pi over 3, that's the key. So pi over 3, pi over 2, 2 pi over 3, pi, 4 pi over 3, 3 pi over 2, and 5 pi over 3. I'm going to tack on a 2 pi here. Oh, and then Aiden, I don't think I answered your question. So we have to graph roses, lemniscates, and spirals. So we should be out of this section tomorrow. Today's Tuesday. Tomorrow or Thursday, absolute latest. And then we have the second half of the chapter with vectors to pick up with, which we haven't even started what a vector is yet. So there's 2 completely different notes of this chapter. One is polar, and the other one is vector value functions. They're in the same chapter. They're 2 completely different concepts inside there. Oh, of course, there's a connection between them, but students tend to think they're 2 independent topics. But there is a branch between them. But yeah, it's not like sits 1 was double angle, sits 2 is half angle, sits 3 was. It's not like that. There's a little bit more of a broader application going on between this polar and vector value functions, which we'll see when we start that hopefully Thursday, but if not Friday at the latest. So we have to finish chapter 8 for this semester. So
for like the theta values, we can use like half of them.
yeah, so to go from 2 theta to theta, take half. So half of 0 is still 0. So what gets put here?
Pi over 6.
So that's what's actually gets plotted as pi over 6, although you evaluated at pi over 3.
So pi over 12 on the graph.
Yes, and we're gonna graph pi over 18s today too. What is this? 5 pi over 6 and pi. So what's wrong with that graph? Yeah, that would make sense then. Okay. No, as long as because I would have done the witch hunt to find it. Okay. So the 2, oh, you can't see the function from here. Oh no, but we haven't answered the question. Why is this wrong? What's wrong with this? Oh, it goes 0 to pi. So what do we need to graph? 0 to 2 pi. So look how many points we have already. So that's what, 2, 4, 6, 8, 9. So we need 18 points here for this graph. Or why are you allowed to flip it over the axis? That's why we did tests for symmetry. So you can use symmetry tests to prove or disprove. I guess you can't disprove, but you can prove it, that a function has symmetry. And since this is a cosine graph, which is, oh, that's right, 2 cosine 2 theta. What do you know about cosine? It's even. Oops, even. So that tells me that r of theta is equal to r of negative theta, which tells me it has polar axis symmetry. So we don't need to graph 18 points. We can get away with 9, then just use symmetry with respect to the polar axis. So let's plot the points we have and then use the symmetry. So the moral of the story is you either can plot 9 points, 18, 27, 36, depending on how many points it takes you to complete a 2 pi revolution, or half of it and then hope there's symmetry. But if there's not a verifiable symmetry based on the tests because they're sufficient but not necessary, now you wasted your time testing symmetry and you still have to make the complete graph anyway. So there's going to be a trade-off between how you want to do it. Now this one, you should know this is polar axis symmetry because it's a cosine graph without having to really show much work here.
So basically, like, if it shows symmetry, you can just do the 9 points, but if it doesn't show symmetry, you can do the 8 points.
But how can you show symmetry with only 9 points with half a graph?
Well, like, you have to show, like, the symmetry test.
Yes, then you can do it. Yes, if you show me the test and it satisfies the test, you can do that. That is true.
Newspaper to the gym.
You'd have to plot all the points. Because you can't just assume there's symmetry without proving it mathematically. Because if it fails the test for symmetry, remember, that doesn't mean it doesn't have symmetry. It just means the test fails to show symmetry. So then your only other method is to just plot the points out.
You had a calculator, could you just graph it and see if it does have symmetry?
You could, but on a quiz or test, the chance of me giving you a calculator is 0 on graphing. So let's plug in this table here. So if I plug in 0 for 2 theta, not theta, what's the R value? 3, 2, right? So if I plug in pi over 3, because I plug in pi over 6, but I evaluated at pi over 3. Cosine of pi over 3 is times 2. That's all you need. You need 2 points. Once you have 2 points, the rest of it should just be symmetric with respect to. Yes. Yep. So cosine is going to decrease until what value? 0, -1, -2. I don't need to plug anything in. That should be right, as long as it didn't skip an angle. Now it should increase until when? 2 pi. So that's going to be -1, 0, 1, 2. So no matter if it's a 9-point table, an 18-point table, a 36-point table, once you put your first 2 points there, the other 34 spots should be filled in within seconds because it just follows the pattern of the symmetry of the unit circle. So let's plot what we know here. So at this point, this column means nothing because the column is used to evaluate R, but it's not used to graph R because you're graphing R theta. So at 0, I have 2. Pi over 6, I have 1. Pi over 4, I'm at the pole. Pi over 3, I'm at -1. I go against the angle. Pi over 2 is -2, so it goes down to 3 pi over 2. 2 pi over 3 is -1, so it's 5 pi over 3. 3 pi over 4 is the pole, already have it. And then 5 pi over 6 is 1. And pi is 2. So that's all the points I plotted by the table. Now, by symmetry, and more importantly by polar axis symmetry, we should say, what points do we get for free here? So start naming some coordinates then. Pi over, or wait, r comma theta, not theta comma r. So 2 comma pi over 6, I heard 1 comma 11 pi over 6? Is that what you said? I agree. Should be quite a few more actually. 1 comma 7 pi over 6, I would agree. So that's this point reflected. That was this point reflected for 11 pi over 6. There should be 2 more. Okay, I already have that up here. -1. 1 4 pi over 3. I already have that. So what would be the? -1 5 pi over 3. I would agree. Or 1 comma 2 pi over 3, which should be right here. I already have 4 pi over 3. That'd be over here. Yes. -1 4 pi over 3, or just 1 comma pi over 3. That would work too. I think that is it. Okay. So I want you to watch me draw it first, then you can draw it. So, and you can start wherever you want. I always start at the first point I plotted, which was at the 0 angle. I think that's easiest. So I need to go here, then pi over 6, and then 0. Let the pencil do the work. Don't fight your hand. Whatever direction your hand wants to go in is the direction in which it goes in. So what I mean is this. I start here. It's going down. Bottom's out there. Now it's coming up. There's your rows. So whatever direction your hand wants to go in, don't fight it. It should be a fairly smooth curve, whatever smooth means. We'll learn about that later on this year. And as you can tell, mine is not symmetric, which obviously it should be for the rows. So it doesn't have to be perfect. Now, it can't have 3 petals. It has to be somewhat accurate for the graph. Yeah. Wait, what was the question?
For the 2 pi column.
Oh, wait, the 2 theta column? Okay.
Is that your red dot?
No, the 2 theta column was just used to find the R values. You always plot R comma theta. So I plotted these 2 columns here. The 2 theta never gets plotted. The 2 theta only gets evaluated. That's why you have to make all 3 columns, because you will use all 3 columns. It's just a matter of what is used to evaluate, what is used to graph. Okay. Well, that one. So we did 2, 3, 4, 5, 6, 7, 8, 9, 10. It looks like we did 12 points there. That's what I said. There's no finite number of points. I can't say 8 is enough to satisfy a graph. It's as many as is needed to give me an accurate graph. It could be, I think we said 8 was fine for cardioids. It might take 15 or 20 for rows. It really might. It just depends on what the n value is, which we'll talk about here in a second, or like I said, we'll talk about in a second. So it's just depends. There's no hard rule for how many points is going to be good enough to graph a rows.
Are you going to do another example of this?
Yes, after you figure out the connection next slide. Does anybody still need this one up? So I'll have you try and come up with on your own a rule for N and A, which you'll see on the next slide what I mean by N and A while I go make copies of graph paper. So I'm going to need 1022. Yeah. And those 2 extra sheets, I mean, you're talking that's what, 16 graphs. That should be enough for the rest of all the graphs we do. Because you only have 4 tonight, and then you have 4 tomorrow night, plus the practice one. So that should be enough. It does. Takes time. Anybody still need that graph by the table up? Okay. Oh, go ahead. I agree. Well, the theta equals pi over 2. So if you tested that first before you graphed any points, then the points that I would plot on my table would be from negative pi over 2 to pi over 2, and then reflected over the y-axis, which is theta equals pi over 2. So the polar axis means it's flipped over the x-axis. If it's with respect to the pole, that means, yes, if I turn the graph upside down, you should see the same exact graph. Think of y equals 1 over x is the best example I can think of, is you should see the same graph if you flip it upside down in terms of rectangular.
You can always just like graph the point and like flip it, so you don't have to like graph all the points and then like.
Only if you verify the symmetry test.
Yeah.
You can't. Yes, if you verify the symmetry test, absolutely, you can flip it over x, y, or origin if you've proved the test. But you can't just assume the function or the equation, not necessarily this isn't necessarily a function. The equation has symmetry. Because if you start flipping it on quiz or test and don't show me the symmetry, to me that's guessing. So I wouldn't, even if the graph is right, it's still wrong, because how do you know that is a valid point without either table or you verify the symmetry? All right, everybody good with this one? All right, you are going to do another one, but it's after what's wrong way. So I want you to explore on your graphing calculator for a few minutes here. A and N. I would really, the cosine's probably better to look at. I mean, you can do a sine of n theta. So these are the 2 questions I want you to answer. Don't go ridiculous with n. I had students in other classes go up to 100 and 200 and 1,000. That's not the point. Keep n reasonable to where you can see a pattern of what n is doing. So try different n values. Try different a values. Tell me what does a do to the graph. Tell me what n does to the graph. There should be, if you do enough graphs, you should see a connection or a pattern as to why, or no, as to what happens. The y somebody asked sits period, we might have to come up with a proof as to why it's true that I don't know. So we'll see. So take a few minutes on that. We'll like go run and make, what I say, 22 copies of the polar grid. This is by, well, you tell me. Explore it. Because that's not always the equation for rows. It depends on certain things here. That's why I want you to explore this out for a couple minutes. Aiden, start us off with what you want to say.
Okay, so if n is even,
Okay, 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 n is even.
then the number of petals will be 2. I call them petals.
No, I like that. Number of petals is 2n.
Yep. But
Okay.
if n is odd, then that's just the number of petals. Number of petals. The number of petals.
All right, Frank, prove that. You have an eye. Are you really?
Oh my goodness.
Good for you. No, because Sitchford asked me why. I don't know. I don't know why that works. I know it does work. So I think it's valid. I think we should be able to come up with a proof for this as to why that is true mathematically.
Frank is gonna finish. Don't drop it.
Are you doing something with double angles here or no?
I'm just trying to see if I can, because my hypothesis is that when you
No, it's lame. I like it.
you have the angle that's opposite, like you reach the peak still 2n times, but it's overlapped maybe, like the points overlap, but
You mean like the ordered pair is like duplicate, like it's hit again, just in a different.
yeah, like
It's written in a different way.
yeah, like pi over 2 1, or 3 pi over 2 negative 1 pi over 2.
Sure. So we will see that when we graph some of these out. We're going to see duplicate. I don't know. Like I said, I don't know a proof behind that. There's got to be a proof for this to be true. I was thinking double. Like I don't know if you convert this to double angles. If there's a way to, I don't know. I like the conjecture for that though. Yeah.
Technically a multiple of 2, so maybe that's why like Haskell brothers do doubling number of n, and up with petals being twice number of n, because every even number is a multiple of 2.
It's a valid point. No, I really think this would be an interesting thing to look into. What about A though? So we have n. That is 100% right. When n is odd, it's number of petals. And when an n is even, it's double the number of petals. So A, give me something here.
I'd say that whenever a becomes higher, it makes the petals big.
Max value. Yeah, it deals with the max. It tells you how. I refer to it as how far the tip of the petal is going to extend. The easiest way, I think I said the cosine graph is easier to use here. I think, am I in polar or am I in? Okay, good, I am in polar. So let's just do a 2 cosine. I think we just graphed 2 cosine 2 theta, didn't we?
Yeah.
And let's just do 2 cosine and 4 cosine. Oh, that, okay. No, that's bad. Okay, hold on. No, that's not cool. That's bad. Why is it not resetting my, there we go. It wasn't resetting, my theta step was too big. We'll talk about theta steps tomorrow when we start doing spirals inside there. So yeah, the tip of the petal here for the 2 theta goes out to 2, and the tip of the petal for the 4 theta goes out to 4. So whatever A is, that is the max or min, because it can be negative, you should see on that. Well done. A couple other rules here, which this is where the proof could get hairy too. N cannot be 0, and N cannot be plus or minus 1. Because if you have a petal or a flower with 1 petal, it's just a circle. And we've graphed that before. We've graphed R equals sine theta. Multiply both sides by R. R squared equals R sine theta. X squared plus Y squared equals Y. X squared plus Y squared minus Y equals 0. Complete the square. And you get the centered 0 comma negative a half if you, or 0 comma 1/2 if you do it with radius 1/2. So N can't be 0 or N cannot be plus or minus 1. Now if N is 0, that should be obvious. You just have a constant value. It kills off the theta. So that should be fairly straightforward. So you have a circle of, well, for sine, you have nothing. You have a point. And for cosine, you would at least have a circle of radius A for that problem. True. The circle itself would be the 1 petal, which means there's a certain, let's see if we can make this connection here. What would be a number of petals that would be impossible to graph? What rows If you graphed me a rose and it had some number of petals, how do I know without looking at anything it's automatically wrong? Sits would work, or 2 would work, sits would work,
Yeah,
10 would work.
it would be any multiple. It would be 2 times n when n is every other multiple.
Would it be 2 plus 4k, where k is a positive integer? Would that sound right, Frank? 2 plus 4k? Okay, good.
I was trying to say something like that just because I was like math. Is it just every other multiple too?
2 plus 4k, same thing. However you want to say it. Every other multiple, sure. Positive element of z in this case. So you can have a negative 2 for that one. So yeah, 2 is k is a positive integer value. That's good. It's really good. All right, so let's graph this 3 theta out. So without doing any work, how many petals should this graph have?
3.
I'm looking for 3 tips. Once I see 3 tips, I know I got enough data for this graph here. So you're going to see this table here. So again, I want the argument 3 theta to be what types of values if it's a sine function?
5 or 6.
5 or 6's. Which means the thetas are going to be what? 5 or 18's. So, and now a couple points I want to make here. Look at how many points this table is, and that still only gets me to pi. So I'd have to double this. So this is what? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's only 13 points. So I'd have to double that to get to 26 to graph this from 0 to 2 pi of the theta value, which means I'd be graphing from 0 to 6 pi of the 3 theta value. So I just said, when I said 20, 30 points, I wasn't joking. It really might take 20, 30 points to get a good graph. Yeah. So, well, yeah, we have to fill this table in anyway. Remember, once you fill in the first 2, the other 34 points should flow right off the pencil, because as long as you understand the symmetry of the trig function of the unit circle, you should know if you're increasing or decreasing by that common ratio. It's not going to go 0, 1, 2, then up to 4. It's going to go up by 1s, down by 1s, up by 1s, down by 1s throughout the whole figure, throughout the whole shape. So once I figure out the first 2, we should be able to blitz through the rest of it. So it's 2 sine 3 theta. Now remember, you're plugging in 3 theta into the function. You're graphing theta. So you got to be careful here. So if I plug in 0 for 3 theta, what's my r value? Zero. Sine of 0 is still 0. If I plug in pi over 6 for 3 theta, what is my r value? There's my ratio. I'm going up by 1s. So I have that. I don't need to plug in another value. I shouldn't have to plug in another value. So it's a sine graph. When is sine going to increase till? Pi over 2, which is my next point. So it goes up to 2, which should make sense because the a value tells you the tip. So once I hit 2, that function better start dropping. So I'm going to drop by 1s until I hit what value? Negative 2, or in terms of theta, would be what? What would be the minimum value for sine? What angle? What was it? 3 pi. Okay, I just want to make sure it's 3. So it's 1, 0, negative 1, negative 2, which is at 3 pi over 2. Now it's going to increase until what point? 2, or what angle? Well, pi over 2 after the revolution would be what? Pi over 2. So I'm going to increase up until here. So how about negative 1, 0, 1, 2. And I'm going to decrease again until I hit 7 pi over 2, which is 1 and 0. Ignore that homework. That homework's not right for tonight. So let's start plotting these points out. So now we got to plot pi over 18s here. So let's think this through. There's 3 tick marks between 0 and pi over 12, which tells me how many, each tick mark represents what unit. If there's 3 tick marks or knobs or whatever you want to call it from 0 to pi over 12, what does each tick mark represent? Pi over 36. So pi over 18 would be where? The second one. So that tells me every 2 knobs or tick marks or whatever you want to call it is a pi over 18. So this is pi over 18, 2 pi over 18, 3 pi over 18, so on and so forth. Let's start plotting this out here. every tick mark is pi over 36. So every 2 tick marks is pi over 18. Because every 2 pi over 36. Where we start the pole, that's easy. So pi over 18, which yes, you're going to estimate this, is 1. Then pi over 6, each tick mark represents pi over 36. Then pi over 6 goes out to 2. 5 pi over 18. Now let's think this through here. So 5 pi over 18. So pi over 6 is how many pi over 18s, if that, you understand what I'm asking? 3 pi over 18. So I'm at 3 pi over 18, 4 pi over 18, 5 pi over 18 right there. So 5 pi over 18, I'm at 1. Then pi over 3, that's easy. That's the pole again. Now this is where it gets confusing. So 7 pi over 18. So pi over 3 is really 6 pi over 18, correct? So 7 pi over 18 is 2 tick marks past that. But I need to go against the angle. So the easiest, because it's -1.
Oh, it's -1.
So I need to go against the angle. The easiest way that I find to do this, find where you're at. So I'm between the pi over 3 and the pi over 12 here. So then just match it down here between the pi over 3 and the pi over 12. Now I'm closer to the pi over 12. So be consistent. Stay near the pi over 12. And then at pi over 12, so this is my 7 pi over 18. So -1 would really be right there. Pi over 2 is -2, which would be down here. 11 pi over 18. So 11 pi over 18. So this is, so pi over 2 is what? 9 pi over 18. So go tick mark, or go 4 tick marks past that. 2, 3. This would be 9 pi over 18 right there. And I need to graph it at -1. So I go between the pi over 3 and the pi over 12, which would be right here. 11. I think I said 9. I need 11. So this is 11 pi over 18 right here. I need to go against that angle, which would be down here, closer to the pi over 12. Is really that point right there. So I go to radius of 1. Pi over 2, I'm at negative, or already had that. 2 pi over 3, I'm back to the pole, already have that. 13 pi over 18 is 1 pi over 18 past 2 pi over 3, which would be right there, radius of 1. Can't see my table anymore. 5 pi over 6 is 2. $17 pi over 18 would be 2 tick marks above pi, which would be right here. That has a radius of 1. And at pi, I'm at the pole. So look at that graph. Is that enough data or no? Why? I see 3 tips. I see 3 petals, so I know I'm good. I don't need to do it from 0 to 2 pi. So you don't always have to go from 0 to 2 pi. And sometimes you don't need to test for symmetry. Sometimes the graph will build itself. So let's start at 0 and build this out here. So my first hit was pi over 18 after 0. Again, don't fight your hand. It wants to go down, let it go down. It wants to go up, let it go up. Oh, I circled too far there. Yeah, I fought my hand there. So then if we graph on a test, no, the test will always be 2 or 3 theta, because I know these aren't easy to graph. Challenge problems?
You make challenge problems like 30 states.
The challenge problem I can make the 6 theta, 8 theta, 10 theta, because you have 2 weeks to, or you have time to do it. Test is a 2 theta or 3 theta, because these take time to graph. It won't be a 4 or 5 or 6 or 7. So we're one sheet front back, couple graphs, 2 or 3 graphs, and then just some conversions for this stuff, and then we'll do the vector stuff, which won't have any graphs. Well, it won't have any graphs like this. It has different types of graphs for vectors. Vectors are easy to graph. They're not hard. Vectors, it sounds hard, but they're not. All right. Let's graph this out. So we said it was, what, 2 sine 3 theta, right? So if we zoom for this, I mean, that's pretty spot on of what this graph should look like. So the tips should be, so there should be 3 tips, and we see the radius of 2 for each of those 3 tips. That's a fairly good graph. All right, what was your homework last night? So 55 through 58, 4 graphs, 55, 56, 57, 58. You're going to see 2 roses. I'm sorry, you're going to see 4 roses. I think 2 of them are sine, 2 of them are cosine. Okay? So I'm not done yet. I got 5 minutes left. I'm going to do lemniscates. Come on, you know better than that. All right. So it's lemniscates. So yeah, we're going to start lemniscates tomorrow, so I might as well start it today. So lemniscates are often called infinity graphs or figure 8 graphs. So and notice the equations. It's hard to see in blue, so I rewrote it down in black down there. So it's an r squared equation. So r squared equals a squared cosine, and it has to be 2 theta. There's no other theta you will see. It has to be 2 theta for these graphs. So r squared, so it's it's the first time we've seen a squared value for these right now. So r squared equals a squared cosine 2 theta, or a squared sine 2 theta. Now for the cosine, again, polar axis symmetry. I mean, obvious, it's a cosine graph, so r of theta equals r of negative theta. We've known that for months now. What else do you notice about the graphs of the cosine and the sine one? Go ahead, Ibra.
Cosine has pole and pi over 2 symmetry, whereas
Okay.
sine has, no, that one has polar axis and pi over 2. The other one
And pole symmetry. We have pole symmetry too. You're right.
Okay, and then sine one has pole.
Just pole symmetry, I would agree. And why do these have pole symmetry? What was the test for pole symmetry? The one we haven't talked about yet. What was it? R equals negative r. Well, if you square a negative, what do you get? So it should make sense why this has pole symmetry for these graphs here. It's good. So the last thing I want to talk about is spirals. We'll actually graph one of these, well, maybe 2 of these tomorrow. They're also known as propeller shaped, kind of like a helicopter propeller. They're in lemniscate patterns for those. If it's not in lemniscate pattern, that helicopter's not going to have a successful, it won't have an equal number of takeoffs and landings, we'll put it that way. Thank you for understanding that. One more takeoff than landing, yes. You'll have n landings and n plus 1 takeoffs. Very good. So this, I'm sorry? So the last one I want to look at briefly for the last... So if you look at the front cover of your book, those of you that have a book, you should see this equation, r equals e to the theta over 5. So that's actually the graph of a spiral. Now, spirals are very easy to graph because these are 100% calculator-based problems. You can't do these by hand. Because you can't plug in a theta and then raise e to the 1/5. You know, it's just ridiculous. You just can't do it by hand. There's no way. So what? It's over 5. E to the theta over 5. This is for spirals. E is a number, 2.718, the exponential number e.
Yeah.
Shh, it's all right. E to the theta, Euler's number. Yes. So, and let's just take a look at these graphs. If I do a zoom 6, it only graphs to 2 pi. Yeah, why not graph this to 8 pi? That's better. So let's graph this from negative 30 to 30. 6 is, let's see if we get a better graph here. Oh, that's good. It's really good there. So we're going to practice doing those by hand, making some tables tomorrow with lemniscates. I assume we'll be going over the roses. I don't think. Those aren't as easy as the limasomes and the, thank you, cardioids. We've been to hearts. How can I forget that? See you tomorrow.